Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, conference participant. It's my pleasure to share my research experience, my research work here in this conference, International Mechanical and Industrial Engineering Conference 2022. My research experience, my research work mostly about engineering optimization, especially for expensive problem. So the title for this today presentation is Efficient Engineering Optimization for Expensive Problem. Here are the outline. I need to present first about engineering optimization. Then next is surrogate-based optimization. Actually, this presentation is about surrogate-based optimization. And the next one, this is my contribution in this area. I will close this presentation with introduce to you some people in optimization. Okay, let's start from engineering optimization. Our engineering product or our engineering system affected by several factors. If we plot the performance of our product or the response our system or the output versus these factors, we will get a curve or a surface. For multidimensional, it will make a surface. So optimization is a method, is a searching algorithm to find the extreme response. What I mean the extreme response? If we are looking for the maximum point, you are looking for this point, this solution. If you are looking for the minimum point, you are looking for this solution. Or this one for a two-dimensional problem. This is global maximum. This is local maximum. So optimization is a method, is a searching algorithm to search that extreme response. There are two main groups in optimization method. The first based on gradient information. If you ever heard about golden section search, Newton-Raphson method, steepest distance, they are all based on gradient information. They start from single trial solution and use gradient information to move to the better solution. This method fast and efficient, but highly likely trap it into local optimum, depend on the initial trial solution. Another side, population-based method, genetic algorithm, particle swarm optimization, N colony optimization, B colony optimization are in this group. Instead of start from single trial solution, this method start from a set of solution, also called population, and use the searching operator, for example using GA, use crossover, mutation, and selection to move to the better solution, a set of solution. So this method has ability to jump out from local optimum, but as population-based method, this method requires a lot of sample evaluation. This is illustration for population-based method. Okay, now come to the surrogate-based optimization. Most of our engineering problem, we don't have mathematical relationship. We don't have mathematical formulation to relate the input variable to the output response. We often use time-consuming computer simulation or costly physical laboratory experiment. We call these two kinds of problem is expensive problem. We cannot use population-based method directly for this expensive optimization problem. Then we need to replace, before we use the population base, we need to replace the actual system with surrogate model. How to build this surrogate model? The surrogate model, some people also call this surrogate model as approximate model or approximate function, or some people call meta model, emulator, or just a model. Whatever you call this approximation, this is approximate based on the data you have. We need some data to approximate the response of the system. How to make this approximation? We can use second order polynomial response surface method, artificial neural network, ANFIS, Kriging, or etc. This is illustration. We distribute sample, we evaluate the sample using the true system, the true function, the actual system, and then we approximate this response for using second order polynomial response surface method, or using Kriging, artificial neural network, or ANFIS, or any other modeling method. When we have that surrogate model, that approximation, we can predict, we can estimate for any untried sample. For example, we don't have data here, but we can approximate the response using this surrogate model. Or we even estimate the optimum point, the minimum point here. Since our prediction based on this approximation, the accuracy of the prediction directly related to the surrogate, the accuracy of this approximation. The accuracy of this approximation directly related to the number of training sample we use to build this approximation. That's why in this flowchart we need to validate the surrogate model first. We need to validate the accuracy of the surrogate model before we capture the optimum. This is two main group in surrogate-based optimization. The idea is similar. Start from sample, construct the surrogate model. But in this type, in this group, they are need to validate the accuracy of the surrogate model first before we capture the optimum. But in this group, they start from initial sample, they build surrogate model, and they capture the optimum and add that verified optimum to refine the surrogate model until meet the confidence criteria. In this type, they never measure, they never validate the accuracy, the surrogate accuracy of the surrogate model. I prefer to use this type. Why? We actually, for surrogate-based optimization, the accuracy is important. But accuracy for the whole region, for the whole location of the surrogate model is not important. The most important to make accurate is in the promising area. If we are looking for the minimum, we make this area, we want this area accurate enough to make accurate prediction. We don't want spend more sample here just to make this area accurate, since we don't want to make a prediction, we don't want to share the optimum here, so we need to spend more sample here, not here. Then how many sample we need to build the initial surrogate model? Since these two type of surrogate based optimization, they need initial sample to build the initial surrogate model. How many sample they need? I think most of the publication in this area refers to this publication, Efficient Global Optimization for Expensive Black Box Function. This paper suggests to use 10 times of number of variables. For example, in this publication, this trust structure optimization, they have 7 variables, 7 design variables. So they need 10 times by 7. So they need 70 sample in total to build the initial surrogate model. But what is the reason with this suggestion? I try to understand using this visualization. This is peak function. We approximate peak function using 10 times 2 number of variable. So 20 sample. So this is 20 sample. We approximate using Kriging model. As we can see here, this approximation is very close to the actual system. So if we predict the optimum using this accurate model, so we will get the accurate prediction. So that suggestion actually try to make initial surrogate model accurate enough. But as I discussed with you before, accuracy of the surrogate model is important, but only in the promising area. We don't want spend more sample here just to make this area accurate, since we are not looking for the minimum point here. We are looking for the minimum point here. So we need to spend more sample here. Using a half of this sample, 10 sample, still accurate, still close to the actual sample. But using fewer sample, for example, using 4 sample, the approximation is very bad. If we predict the optimum based on this inaccurate approximation, we will get a false optimum. So intuitively, if you get this inaccurate approximation, you will scrap and refine this and rebuild this surrogate model by adding more sample. So what can we do with this inaccurate sample? Let's take a look closer here in this dot is our sample. This value of in this location is the true value because we have sample here. Closer to this sample site, the prediction is still accurate. But farther away from this sample location, the prediction become worse. The analogy is something like this. In the location you are standing right now is raining. If in your location you are standing right now is raining, then 2 meters away from your location, 2 meters close to your location, highly probably training to. But farther away from your location, for example, 2 kilometers from your position, we will not make a prediction very accurate. So instead of searching the optimum farther away from this sample site, we limit the searching region for the optimum only around this sample site. How to limit around this sample site? That is the difficult one. Kriging modeling. This is Kriging prediction based on 10 sample of peak function. Kriging modeling provide estimation error of prediction. Error in the sample site is 0 because we have sample here. Error near the sample site is small, but farther away from the sample site, the error increase. So we cut this level of error. We only shoot with a smaller level of error. So we use this estimation error of the prediction to limit the searching region. So this is a peak function. This is prediction of peak function. This is the sample site. This is the estimation error of the prediction. We pick a level of this estimation error and project it here to define the searching region. Instead of searching farther away from this location, the sample site, we limit this. So we search this point instead of too far from this sample site, because this is the error of the prediction is larger. So then we verify this prediction using the actual system and refine this surrogate model, this approximation, and redefine this searching region and repeat the process. So the approximation, the surrogate model will evolve during the optimization, and also this reliable region, this searching region will expand or shrink dynamically based on the accuracy of the surrogate model. Here the illustration using peak function. This is approximation surface response plot of this peak function based on 4 sample here. This is the same thing like this, but this is the contour plot. We also plot here the searching region. So we search for the optimum inside this reliable, we call this reliable region. We will get this prediction. We verify this prediction using actual system and refine, add that sample to the training sample and refine the surrogate model and repeat the process. Here is the process. The surrogate model evolves iteratively by adding one additional verified sample. Now we capture the local optimum here. We still get this optimum. Now we explore another area to search another promising area. We get this global optimum. We capture the global optimum here. So now it jump out to global optimum. As we can see here, we didn't spend a lot of sample in this non-promising area. We only spend more sample to refine, to make this promising area accurate. So our prediction is accurate to the global optimum. So these features make this optimization method very efficient. So this is the main flow chart of this method. Starting from the sample, training sample, we collect the sample using design of experiment, and build the kriging model, the approximation, define the searching region, call the optimizer to search for the optimum based on that approximation, repeat the process, verify the prediction, and redefine the reliable region using fuzzy inference system, and repeat the process until convert to the prediction. If the process convert to the prediction, it means that we capture the optimum, but we need to explore another area to search the global optimum. Exploring another area using maximum expected improvement until no other optimum we can find. So we then stop the process. Now we get the optimum. I need to explain what is maximum expected improvement. This is exploitation sample. I don't want to discuss this exploitation sample and exploration sample. We use expected improvement criteria to explore another area. What is expected improvement? Expected improvement share similar concept with probability of improvement. So easier to explain in probability of improvement. Okay, this is the sample we have, and this is the prediction. So the current optimum is this point. The prediction in this site, for example, we will get this point, but we also probably get this value here, or here, or here, or here, or even here. So the probability density function of prediction in this site is so the probability to improve, to get better value from the current optimum is this probability. So we find the location of sample here with maximum improvement, probability of improvement, and add that sample to the training sample to explore another area. These features make this proposed method is more efficient. We evaluate our method using numerical benchmark test function. These two different extreme numerical function. Spare function is smooth function, only one global optimum here. And this ugly function is an ugly function with single global optimum around so many local optimum here. This is two-dimensional problem, just for illustration, but our method evaluate using this function, but for 20-dimensional problem. We compare with similar method in the literature. We get better solution, but not only that, we spend fewer samples, so our method more efficient compared with the method in the literature. We also evaluate our method using engineering problem, trust structure efficiency. I adapt this problem from this publication. This publication is in Journal of Mechanical Design. This is a good journal, Q1 journal in optimization, in engineering mechanical design. The objective of this problem is to maximize thrust efficiency. Thrust efficiency is maximum load that can support with this structure without fail, divided by its weight. So this is the thrust efficiency affected by function of 7 variable. This 7 variable is the location of this point. And subject to allowable stress, axial allowable stress, and buckling criteria. This is variable space, variable ring. Okay. This publication, their work, got this result. Our work got this design. So we got better design compared with their result. Not only that, we also spend fewer sample compared with this sample in total. Okay, but 3 months ago, I received notification that this paper cite my publication about this problem. They got similar design actually, slightly better than our result. This is our result, this is their result. But they spend fewer sample. We spend 87 sample in total to get this result. They only spend around 56 sample to get better design. That's okay, that's very common in this area. Okay, another application of this method we apply for this light guide bar design. For conventional auto lamp using direct light. For light guide plate, they use reflected light. The basic principle of this light guide bar is from this light source, the light travel around this along this medium. Some light will reflect out from this V-cut. So the objective is to find the geometry of this V-cut and the distribution of this V-cut so that the light will travel and reflect out here uniformly. So this is the initial design. This is the optimum design we got from that method, the proposed method we discussed before. We also apply this method for deep drawing punch design. They put micro reeds here to improve drawing ability of sheet metal. Without micro reed, for conventional punch design without micro reed, the stress will concentrate here. But by adding micro reeds here, the stress more uniform distribute along this sheet metal. So this micro reed improve the drawing process. But logic, since we put micro reeds here, then the force to pull out this punch tool from the drawn part become larger. That is negative side effect of this micro reed. So the design objective of this micro reed is to minimize the thinning rate so we can improve the drawing ability, but also we want to minimize the stripping force so we can easily pull out this punch tool from the drawn part. But from the data, the thinning rate and stripping force is conflict to each other. When we minimize the thinning rate, the stripping force increase. When we minimize the stripping force, and the thinning rate increase. So we solve this problem using multi-objective, but we convert the two objective using fuzzy inference system. So we measure the combination objective we call design fitness, fuzzy design fitness. Okay, here the result. Here the result. We compare with Taguchi's method. Our method our method get similar design. This is similar design with Taguchi's method, but in terms of fuzzy design fitness, we get better design compared with Taguchi method. We also apply the method for robust optimization. There are two things we need to consider in robust optimization. We need to optimize the mean response because our product performance or our engineering system uh, under influence of noise factor will fluctuate around the, so the objective of robust optimization is to optimize the mean response and to minimize the variation. So this design objective is to make this target sensitivity is on this target and to minimize variation of beta because of noise factor. So we have 5 control factor and 11 noise factor. For these kinds of problem, usually Taguchi use L18 to accommodate 3 level 4 control factor and L16 for 2 level 11 noise factor. Taguchi use cross orthogonal array to estimate the variation of this design. So Taguchi's method will require at least 288 sample in at least sample. I need to talk a little bit about robust optimization. There are two quantity you need to consider in robust optimization. The mean response, the central tendency. We need to optimize this mean response. And also we need to minimize the variation of this response. So these two things, these two quantities need to consider in robust optimization. For nominal the best problem, Taguchi's method proposed two-step optimization. From this initial design, they try to find the most robust design with a small variation. From this step, then using scaling factor to move the mean response to the target. Ideal scaling factor. Ideally, the scaling factor not affected the variation of this solution. So that is, but in actual situation, the ideal scaling factor often hard to find. This is another critic to Taguchi's method. So we solve that problem using Taguchi's method, of course, and using our method when we compare. We always almost got similar solution than Taguchi's method. Our solution slightly better than Taguchi's method. Taguchi method find the mean of that sensitivity closer to the target, but our design is better in terms of mean square error. Not only that, we also spend fewer sample compared with Taguchi's method. We also apply that method for aerodynamic shape optimization, for airfoil shape optimization to increase lift coefficient, and also for propeller blade design optimization to increase thrust force of this propeller design. Okay, this is the last part. I will introduce to you some people in this area so you can update and follow their work to understand more about this topic. This is Agus Sujianto. He was born in Kulon Progo, Yogyakarta. He spent his career after graduated from uh, a doctoral degree, mostly in United States. He was a product design manager in Ford Motor Company before moved to Bank of America, and now he is with Wells Fargo. Wells Fargo, the oldest bank in America. I love his work. This book, Design and Modeling for Computer Experiment. And this is Pramudita Anantapalar. He is with Institute Teknologi Bandung. He graduated from Aeronautic Engineering University of Tokyo. He also worked in surrogate-based optimization. This is one of his publications on the use of surrogate model in engineering design, optimization, and exploration. This is Alexander Forrester. He is with a university in United Kingdom. He is in computational engineering department. I love his work, this work, engineering design via surrogate modeling. And this is Yao Jin. Yao Jin is a lecturer in a university in United Kingdom and also a lecturer in a university in Germany. I met him in 2019 in an international conference. Yao Jin also worked on surrogate-based optimization. If you are interested in multi-objective optimization, follow their work. Kalia Mondep and Carlos Cholo Cholo. Now Kalia Mondep is with State University of Michigan. He is in mechanical engineering department, and also he is in electrical engineering department. Okay, for the conference, if you are interested to attend a conference in this area, in this specific area, there are at least 3 big conferences in this area: CEC, GECO, and SMC. That's all for my presentation. Thank you for listening.